Hello everyone and welcome to We Meet at EMC Digital Days. My name is Marie-Therese Kohl and I will moderate this presentation. We are very pleased that you took the time to participate in our virtual conference. The topic of this presentation is why EMC is a headache and how to avoid it. Our speaker is Arturo Mediano. He will hold the presentation and will answer your questions. But before we start, I would like to point out one thing. You will be muted during the presentation. This means that you cannot ask questions via microphone during the presentation. Nevertheless, you have the opportunity to ask questions during the presentation at any time via the chat function. And you will find a chat function in the webinar control panel. This presentation will be about 1 hour long. The chat questions will be answered in a Q&A session following the webinar. There are 5 to 10 minutes in addition scheduled for this. And if we are unable to answer all your questions within this time, we will answer them via email afterwards. If you still have any other questions left, just mail us at exhibition@we-online.com and we will try to answer all of your questions promptly. At the end of the webinar, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our event. And you will also receive the link to this presentation in the next few days, and the recording will be available at our website shortly. But now I will hand over to our speaker, Arturo, and I wish you all an exciting presentation.
Hello, and thank you for your nice introduction. Can you confirm that you're listening?
Yes, we can hear you.
Okay, so thank you again for your kind presentation, and I hope all of you will enjoy the session. Really, you will enjoy the full week, this nice event organized by Würth Electronics. And I had the opportunity to talk about EMI and EMC in general. Nothing especially technical like in the previous sessions, considering the filter, the ferrites, the filters, the DC-DC converters, and things like that. I will try to talk about the general ideas in EMI and EMC that create a problem that for today companies is very, very big. I am Arturo Mediano. I am in Zaragoza in Spain, and my laboratory is called the HF Magic Lab. I have explained previously in previous seminars. The idea of the HF Magic Lab is to mix the HF, high frequency, where you find problems related with EMI, electromagnetic interferences, or electromagnetic compatibility, what we talk about when we talk about EMC, or when you are interested in signal integrity, or in radio frequency, if you are introducing Bluetooth, Wi-Fi, radio frequency systems to communicate wirelessly. There is a lot of possibilities when you are working in high frequency, and especially for some companies that have not knowledge in this field, some of the problems are considered like magic. You have seen this idea in some books or articles, but really it's not magic. You need to learn about the basics of radio frequency, and probably you will solve or you will avoid a lot of your problems. So we will be talking today about EMI and EMC, but remember that the fundamentals of physics are the same if you are suffering problems in signal integrity or in radio frequency appliances. Well, let's start with what is EMI and what is EMC. Obviously, many of you knows about that, but let's make a general review. The idea is that today we have a lot of electronic components, electronic instruments in our environments. We are designing, I don't know, home appliances, automotive systems, or audio systems, or lighting, a lot of different electronic circuits. When we are designing a system, I don't know, for example, a toy, perhaps we are not considering how this toy will be working when in the same room like a medical appliance. This is the idea of an ideal world. We can design circuits, we can design products without consideration with other applications. But what happens in a real world? In a real world, we start to have problems. These products that are in the same environment, in the same room, in the same building, start to create problems. The first idea about problems with electromagnetic energy was called RFI. RFI was the acronym for radio frequency interference, where the problems appear in radio receivers. When the television appears, the problem was called TVI, television interference. And when in general, we consider that any kind of product, not only communication systems, can be affected by electromagnetic energy, we talk about EMI. So EMI is some kind of a general idea of creating electromagnetic problems from one kind of products to another kind of products, not only communication receivers or communication devices. Let me show you a video. This is a video in the kitchen of my home. You can see this is a TV. The TV is not working. It's a digital TV. This is a typical failure when you are trying to see TV in an environment with a lot of noise, because the product is failing. Usually in the environment around the product, more or less closer to the device, we will find another product. In this case, is the telephone that is being charged. The problem that we have here is an EMI problem, because one of the products, the telephone, is creating problems in the other product, the TV. And the coupling mechanism is the radiation in this case. So a typical solution to solve the problem is to put far away the victim from the culprit. So you see, I take the phone and I put the phone far from the victim, and the victim start to work. This is the kind of problems we try to avoid when working in EMI and EMC. Of course, there are other different problems that the designer or the manufacturer of electronic circuit need to afford, like, for example, safety. You can see, to avoid electrocution, or to avoid fire, or to avoid explosions, or you need to take care about environmental design, or you need to take care about standby consumption. There is a lot of things to consider. Many of them are related with regulations that makes to create a product that is safe, that is good, that is, how to say, that will not create problems in the field is not so easy. No. So let's see how is the general problem with any EMI problem. The first idea is that you will find a culprit. A culprit can be any electronic circuit. I am considering a TV receiver. Sorry. It's a victim. The victim is the TV receiver. Now you need a culprit. The culprit can be an intended culprit. I mean, for example, a system that is created to radiate energy to the environment, like, for example, a walkie-talkie or a wireless telephone. Or, for example, you can have the noise coming from another kind of culprit. Any electronic product can be an intended culprit. So the electromagnetic energy go out from the product through the air. Okay, the possibilities to have this energy going from the culprit to the victim is through the coupling mechanism. The coupling mechanism in this example is through the air, is non-conductive. But we have another additional possibility: the possibility to have the culprit and the victim connected through the mains network, or through the power supply network, like, for example, DC levels in automotive business, or AC in home appliances. Then the noise from the culprit goes to the victim through the mains cable, through the power supply cable. This is what we call conducted emissions, and both of them must be limited. In this idea, we arrive to this general perspective about EMI or EMC problems. We have emission problems. In that problems, our product is creating electromagnetic energy and sending this energy in a radiated or a conducted way through the air or through the power supply cables. Or we have the possibility to have immunity or susceptibility problems. In this case, we are worried about the radiated and the conducted EMI that is coming to my product and is creating a reset or a failure in any kind of problem. So let's see the problem in a more general point of view. This more general point of view thinks in this way. This is your product, the orange square. And then part of the energy I am working with in my product go away. Then At some distance, we have another product, and this product failed. This is what we call EMI. This is what we call EMC. Later, I will explain the difference between EMI and EMC. But there are two additional problems that not many people know about that. The first one is when this energy is able to arrive to some people or some domestic animal or something like that, no? Your dog or any kind of horse, something like that. The problem is that perhaps this is a problem for the safety, for the health of these people. This is what is called EMF, electromagnetic fields. And this electromagnetic energy usually is higher than the previous one, that problem for the EMI or EMC, and is limited by regulations. And additionally, we have the possibility to have electromagnetic energy going away, and the possibility to have some kind of non very good guy, like for example, a terrorist or some kind of people trying to steal money or critical information with one antenna. And at some distance, we can recover the energy, we can recover this information, and we can have some kind of problems with our confidentiality. No, this is what we call, for example, tempest in the military point of view. Okay, so let me show you very briefly one example. This is a very nice example where you can see one antenna. We have two computers, two screens. In one of the screens, we have this kind of image. This is created with shapes, different shapes, big numbers, and things like that. And at some distance, we have the antenna. We can put the antenna at 3 meters or, for example, in another room. And with the energy that is radiated from the first monitor, we can reproduce in the second monitor what we are in the first one. So we can make something like a spy. This is a very important problem. It's related with EMI, it's related with EMC because the fundamentals are exactly the same. If you replace the computers by people, perhaps the energy, if you receive some specific frequencies a lot of time and with some specific amplitude, you can create health problems. This is the EMF problem. Another important problem related with EMI and EMC is directly EMI, is the sensing. If you are in the business of introducing a radio frequency system in your product, Bluetooth, Wi-Fi, Sigfox, any kind of standard you are trying to use for communication, wireless communication, you have the possibility to interfere the radio system with the noise created in your product. DC-DC converters, power electronic circuits, digital clocks are usually the most important sources of this kind of EMI. And then your product will fail because the energy that is in your aggressive area is able to arrive to your GPS or to your radio frequency device, creating a signal to noise ratio that is very bad for communication, for the stability of your communication. So the general idea about EMI and EMC is not only the idea of passing emissions and immunity tests. This is very important. The important idea is that this non-controlled electromagnetic energy can create serious problems. And we need to try to design and to manufacture products to minimize this problem. So you can see here the general resume. For example, we can create intentionally or unintentionally the problems. We can radiate or we can inject intentionally or unintentionally, and we can create different problems. For example, one product can fail. This is EMI. For example, we are not able to pass test. This is EMC. Third, we can send electromagnetic energy to users or to workers around some specific area. Think about a hospital area or some kind of specific industrial product, no? Some specific furnace or something like that. And additionally, like a last option is the possibility to lose confidential info. For example, if you are worried about or you are working with security information for your country or for your company, or for example, you are working with money, like for example, is the situation with banks, no? So what is EMC? EMC is some kind of gap that is trying to avoid a conflict that was appearing many years ago. So the idea is that electronic products are creating a very, very increasing level of emissions. More products working at higher frequencies and around our rooms and our buildings everywhere. What happened with the technology? The technology is more aggressive, working at higher frequencies with lower rise times and fall times, or working with frequencies including antennas. So we radiate Bluetooth, Wi-Fi, blah, blah, blah. And what happened with immunity? Immunity is going down. The products are more and more sensitive every day because we are going from, I don't know, levels of 0 to 12 volts for 0 to 1 in digital electronics many, many decades ago to the 0 to 1 volt to make a difference between the 0 and the 1 in the same digital circuit. So today, electronic is smaller. Today, electronic is faster. Today, electronics is working with lower levels. That means today, electronics is more sensitive. So what is EMC directive? Is the possibility to avoid this conflict. The EMC directive is trying to avoid the conflict, limiting the maximum levels you can inject in the environment and limiting how sensitive you are to the electromagnetic environment that is considered normal in homes, residential areas, industrial areas, medical buildings, or things like that. So let's see how is the definition. What is electromagnetic interference? Electromagnetic interference is the problem. Is any signal that is in your circuit and is not your signal and is creating problems. This is not noise. Noise is similar, but is not necessarily creating problems. Every electronic circuit has noise. But when the noise is creating problems, that is EMI, electromagnetic interference. And what is EMC? EMC is some kind of possibility to demonstrate or some kind of label to indicate that your product will not create problems or will not suffer problems in some specific environment. This is a legal concept, marketing concept. This is a political, economical concept, but really is something that we need to define. So usually governments, big companies create committees to establish where these limits are and how are the environments where we need to measure these limits. Who is affected by EMI and EMC? Really any kind of product, any kind of electronic product, going from home appliances to lighting systems to medical devices, home appliances, automotive sector, power electronic sector. Especially in the power electronic sector, we have a strong source of EMI sources. No, think about any kind of power electronics for the new green energies, lightning, motor drivers, the electric car, battery chargers, travel adapters, wireless chargers. Any kind of electronic product today working with power electronics has the possibility to create aggressive environments. But additionally, don't forget about immunity. Any kind of problem, any kind of product, sorry. And of course, power electronic circuits can receive electromagnetic energy and can fail. So let me show you two examples. No, there's a lot of examples in specialized magazines, or if you go to YouTube or Google, you will find a lot of information. No, for example, this example from the Toyota building, where FCC in the USA ordered to turn off the lights because they were creating a strong electromagnetic energy in the area, and the LTE communication were stopped. No, this is typical from big lighting systems that are installed around, for example, or close to an airport, and you can destroy the communication in the airport. If you see in the right side, you can see that in 2018, more than 4,000 events were detected by the German regulator. Obviously, they are failures that are detected because they involve serious dangers, like, for example, air traffic, radio communication for emergency services, for police, or things like that. But in our typical day, in our homes or in our office, perhaps we are suffering these problems, but there is no specific notification for the government about these problems. No, we suffer the problem and we try to solve as we can. No, but this is a very, very increasing problem for the future. So how EMC is confirmed for a product? This is a very important thing for the manufacturers. They need to do tests. When we are trying to make tests, I will explain this later, but test for the manufacturer means we need time and we need money. This is the two big important elements about testing. We need to go to an external laboratory. We need to take time to prepare the prototypes, to go to the laboratory, to measure, to see if we passed, and to go again if we are failing, blah, blah, blah. So, for example, two typical tests we can do with our product. We take our product and we put the product on top of a table, a typically non-metallic table. In some specific position, we put a line impedance stabilization network. And we are trying to measure how much is the noise we are injecting in the mains cable from my product is the same if you are in the DC power supply, like in the automotive business. We are trying to measure this noise, but the line impedance stabilization network block the possibility of this noise trying to go out and send the noise to the instrument we are using for measuring. Okay, this is typically a spectrum analyzer or an EMI receiver, or perhaps an oscilloscope with a good FFT. The result is something like you see in the right graph. No, for some specific frequency range, let's say 150 kilohertz to 30 megahertz, we will be able to see the limits, and the emissions from my product must be below the limits. How much? It depends on the product, but my recommendation is usually be below the limits, something like 6 dBs, to be sure that in the full frequency range and to be sure that the full production will comply with regulations independently of the laboratory where you are measuring. Radiated emissions are similar. They will take your product and put the product on top of a table, a non-metallic table. They are interested in the energy that is going out of the product at some distance, typically 3 meters, 10 meters, 30 meters, it depends on the product. No? And with one antenna, we usually measure the electric field. It's not necessarily the magnetic field in many regulations, because from the electric field in the far field, we can estimate, we can calculate how vast is the magnetic field. The electric field that is picked up by the antenna is measuring like a voltage. And this voltage is plotted in a frequency range, for example, 30 megahertz to 1 gigahertz, and is compared with some specific limit. So if you are over the limits, I don't know, 10, 20 dBs, this is a big failure. If you are, for example, in this situation, this is not a good situation, but it's easier than failing in a broad frequency range. And if you look at this is a dangerous situation. If you are in a small company, probably when you are below the limits, I don't know, 0.3 dBs, 1 dB, you will say, we pass. Be careful about that, because next day, with the same product in the same laboratory, you can be something like this. No? There is the possibility to have differences, non-repeatability in the measurement. That is because my previous advice of being 6 dBs below the limit. Remember that in this situation, the product is rotated 360 degrees and the antenna is going up and down and is rotated to horizontal and vertical polarization. What we are trying to find is in this frequency range, where is the maximum radiation aggressivity of the product. And when we are trying to evaluate immunity, it's the opposite. With the antenna, we inject energy to the product and we see the product fail, or through the mains cable, through the power supply cable, we inject noise in the product to see if the product will fail. And this is the typical result. The typical result, for example, can be something like this. where in the frequency range of interest, our emissions are over the limits 10, 20, 30 dB at specific frequencies. And then in the company, we need to establish, we need to find where this energy is coming from. No, we go to the peaks and we see that the frequency is blah, blah, blah. And we think if this frequency is part of our design, it's a clock signal, it's an harmonic of a clock signal, it's a frequency related with the driving of my IGBTs, or is some kind of parasitic resonance or parasitic oscillation in my circuit. This is what we call troubleshooting or EMI debugging. It's something like an art, and it's not very difficult. It's not very easy for novel designers. Well, remember, sorry. Remember, every time you change the design, every time you change something important in the product, probably you will need to retest. And remember, if you need to retest, you will need time and you will need money, euros or dollars. No? So be careful about this strategy. Why, in general, is a headache the EMI and EMC? Let me write some things, and we have explained some of them before, no? But obviously, if you fail in your test, you will have delays. If you need to make a lot of different tests, you will need time in weeks to prepare the prototypes, to go to the laboratory, to measure and to retest if failing, blah, 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 until you have the full product tested. Then you will have unexpected cost. One of the most important is not only the cost of the solution, this filter or this shielding you need to introduce in the product. One of the most important costs that usually many small and medium-sized companies discover is the cost of testing. Don't forget to calculate the cost of components, the cost of testing, to go to a laboratory for measuring. Obviously, I am including the cost of the components or the elements to have a solution. Another important problem that creates headache is the image degradation. If you are trying to sell to a customer and the customer is explaining they want to pass some specific test and you are not able to do this, or you send the product without complying these limits, then you will not be seriously considered for a good business. No. Two additional important problems for specifically for the designers is size and weight. Many times the solution for EMI and EMC problems is to introduce a filter or to introduce some kind of shielding that is big. There is no space for this element in the product because we are very advanced in the design of the element, and additionally this element is heavy. No, so if you are specifically interested in a light system, in a light product, this will be a serious problem to solve. Another important thing to consider that EMI is a headache is that this is a difficult subject. Why is it a difficult subject? First, because you need to learn the secrets of high frequency design. The secrets of high frequency design have been traditionally in the hands of radio frequency designers, designers of transmitters and receivers in radio systems. They talk about decibels, transmission lines, matching, mismatching. They talk about parasitic elements, parasitic effects, parasitic coupling of electric and magnetic fields, blah, blah, blah. But for the low and medium frequency applications, the high frequency effects are not well known. So this is one of the most important problems for the designers or for the companies. The second additional difficulty for the designers is that you need specific instruments with specific measurement techniques, and this is not easy to learn. And finally, because of all of these lists, usually in the companies with EMC problems, they have a stress. So people is nervous, the delays and the extra cost are difficult to explain or to consider. So usually when I have been working especially with small and medium-sized companies, the stress is one important thing to consider. Why is difficult EMI and EMC, technically speaking, not about cost or time or things like that? The first important thing I consider that is difficult related with EMI is that we see the world as we are. I mean, we try to understand things in our circuits considering how we were learning at the school. No, if you are an industrial engineer, mechanical engineer, a physics people, or an electronic engineer, a radio frequency engineer, all of these people is trained in a different way. Usually, the different fields are not mixed, so the different points of views are not shared between them. So this is a problem, no? A typical example I usually teach in my courses is the idea of using Kirchhoff as Maxwell, no? If you are working with the Kirchhoff point of view, the idea is that the professor tells you that applying here a voltage, we have a current that is going through two wires or two traces like water in a tube, no? So you go to your circuit and you understand that the current in different parts of your circuit is circulating through the traces or through the wires in your cables. This is one point of view. It's very, very useful for designing circuits. You can calculate power by multiplication of voltage and current, or we can work with the concept of impedance, like a ratio between the voltage and the current. But what happened in the other point of view, the point of view of high frequency? We will be working with electric and magnetic field. This is electric field that is going from one conductor to the other conductor. The additional element we need to have a full picture of the problem is to plot the magnetic field. Look at this. This is the magnetic field around the different areas of the wires, the traces, or the conductors. No, so you learn from Maxwell theory that if you multiply electric and magnetic field, you will obtain. You can do this at home. You obtain a vector that is the Poynting vector. The energy is going from the left to the right. But look at the difference between the first point of view and the second point of view. In the first point of view, we think that the energy is going inside of the conductors. In the second point of view, the energy is going around the conductor. The conductors are only some kind of guide to send the energy from one point to the other point. So if we go to our point of view in our circuit, you need to consider that magnetic and electric field are like some kind of fog around my circuit. If part of the energy of this fog is able to go away, we have a radiated problem. And to have a radiated problem, you have in your product antennas, unintended antennas. This is the general view of circuits. So if we see how is the result of a product that is scanned, this is the scan done with a EM scanner from YIC Technologies. If you find how is the energy around your PC board, you will see that the energy is spread around some specific area. If the energy is not controlled, if the energy is not concentrated in the area where this energy must be to do the work, then you will start to have EMI problems. That is because I like to see in this way you and your signals. Your signals is like the lion, and you is the people that is trying to control the lion. No, if you control your signals, you will have the lion under control. If you don't control your signals, you will have a not very good end in the film. Okay, so remember, energy is not going inside of conductors, inside of components, inside of wires. Energy is going around your circuits. Another example, because of this, is difficult. Look at this example. This is a PC board with a chassis and a ground plane in a PCB. My question is the ground plane connected to the chassis or not? Many people will say yes, because I have this wire from the ground to the chassis. And the answer is it depends. Many things in EMI and EMC are answered with it depends. If we see here a chassis, at this point we call B. At this point is called, and this point is called A. You will see that between A and B, we have inductance. Oh no, let me simplify. Instead of trying to plot. Let me plot here. This is the ground plane, okay? So the first idea is to represent where is the wire. The wire is, this is A, this is inductance. You can consider 1 nanohenry per millimeter, something like that. But additionally, between the chassis and the ground plane, we have a capacitance, this capacitance here. So what is the difference between is connected or it depends? If you say is connected, that means that it's connected always for any frequency. But in the real model of the problem, you can see that the ground plane and the chassis is connected only in DC and low frequencies, because the low impedance of the inductance create a low impedance connection. But at high frequencies, this inductance start to increase in impedance. And at some frequency, this inductance and the parasitic capacitance will create a resonance. And the inductance and the capacitance in parallel means a high impedance resonance. And at higher frequencies, the short circuit between the ground plane and the chassis is created by the parasitic capacitances. So the impedance between A and B is something like this: low in low frequencies, low in high frequencies, and high at the frequency where the resonant effect appears between L and C. That means what? At some specific frequency, you will start to see problems in radiated emissions or in immunity, and you will not understand why. And if you move the distance between the chassis and the PCB, or if you change the length of the wire, you will see that the frequency change, and then the problem appears or disappears. That kind of effect is what give EMI the idea of magic. Because if you are not familiar with this effect, you try to solve the problem by trial and error, and sometimes you will not be able to find a solution. Let's go to the general EMI picture to be able to work in a good way. Remember, we need to have a culprit, we need to have a victim, and we need a coupling mechanism. So I have prepared to finish the presentation several suggestions for success. Obviously, this is not magic, and you will need to do a lot of work, but at least you will try to minimize problems in this way. The first idea, suggestion, first, try to think in EMI as soon as possible. If you find or if you think in EMI at the beginning of the process, like this, in the design stage, there is a lot of things to do, very cheap per unit of production. For example, how you put the traces, where you put the components, where you put a small ceramic capacitor, how many, components you use in a filter. If you find the problem in the production stage, there is not a lot of things to do, and these things will be very expensive because you are introducing a filter that is, 10 euros per unit of production, €1 per unit of production. And this extra cost can be a problem specifically in sectors like home appliances or automotive, okay? Obviously, if instead of failing in the development or in the prototype stage, you fail in the installation, I mean, your product is going to the field and start to fail when it's installed, then the cost of the problem is difficult to calculate, okay? Because we mix the technical problems with the image problems or things like that. Second suggestion, work as slow as possible. That means switch as slow as possible. If you switch very fast, that means problems. Many systems today are switching fast as possible, and they are interested in things like efficiency. Example, power electronics. But remember, the maximum frequency of your signals is related with the rise time of your signals. The maximum frequency of your signals can be considered or estimated like 1 over pi TR, where TR is the rise time or the fall time of your signal, the smaller of the values. So, for example, in the picture, you can see my digital. You can think about power electronic signals. You can think about any kind of signal for this example. When I go to a slower rise time, the bandwidth of the signal decrease a lot. Decreasing a lot the bandwidth of the signal means that you don't need to learn radio frequency in a very strong way. You will not have problems with the connection. You will not have problems with your wire. You will not have problems with traces. Well, really, not you will not have problems. You will have less problems, okay? Because problems appear always. Vale? Okay? So switch as slow as possible. Work as slow as possible. If you cannot work slow, if you cannot switch slow, then the solution is learning radio frequency topics. If not, by trial and error, it will be very difficult to find a good problem. Let's consider history. When IGBT was introduced in the market, that increased the emissions around 40 dBs. Why? Because the voltages to switch were 5 times the previous one, and in a turn-off time that was 20 times lower. So the mixing, the increase in voltage with the decrease in time, the DVDT, with a strong DVDT, we have we are multiplying 5 by 20. That is 100. That is 40 dBs in emissions. So one example that what will happen probably in the next years is happening yet in many prototypes is with the new technologies, like for example GaN. We can expect an increase in 20, 30 dBs, and it will be more important, this kind of radio frequency ideas of layout, shielding, filtering, blah, blah, blah. Suggestion 3, you need to measure and you need to simulate if possible. Measure is necessary. You need to buy instruments, probes, for the frequency domain, for the time domain, for electric field, for magnetic field, for voltage, for current, is the only possibility to understand. Remember a sentence that is very good. If you can see it, you can fix it. If you cannot see your problems, it's very difficult to dominate or to solve the problem. And if you can introduce simulation in your process. Remember, simulation in EMI is very difficult because there is so many parasitic effects. There is so many sources and so many factors that you need to introduce in the models that you will need a lot of work to make the system working. But there are today solutions in the market going from the component to the system level simulation. And you can learn a lot from very good problems simulated with this kind of electromagnetic simulators. And additionally, you can simulate small problems or small couplings in some specific areas of your product, not only considering the simulation of your full product. Suggestion 4, you need to dedicate a lot of time to partitioning or placement of components in both the system PCB and the full product. You need to consider where you put the power supply, the oscillator, where you put the audio area, where you put the Bluetooth section. For example, if you look at the graph on the left, you see my distribution considering that there is a connector. So my question is this distribution good or is bad? Low, medium, and high frequencies? And the answer is always, it depends. For example, if you have in this connector, you don't need in this connector the high frequency signals, this is a bad distribution. Why? Because the low frequency signals trying to go to the connector or the medium frequencies will be corrupted by the high frequency. In this situation, it's better to put the radio frequency far from the connector, far from the cables, and then the emission and the immunity problems will be reduced. But it's the opposite if the radio frequency or the high frequency signals need to be connected to the pins of the connector. Then it's better to put the radio frequency area close to these elements to avoid the radio frequency signals going through the full PC board, creating crosstalk or radiation from the PCB. So you need to take time to consider this, and sometimes you will need to test some prototype. I like to consider this similar, no? The PCB, the system is like a city, no? You have a power supply, release or power electronics. This is similar to industrial areas or the dump, no? What is the area that is quiet and sensible? Consider, for example, low-level analog signal. This is something like the hospital or the school. In your PC board, you will have something like connectors to go in with signals in and out. So it's very important. The connectors is the areas where the traffic is going in and out of the city. So you will try to put the inputs to the industrial area far from the hospital or the school to avoid the big trucks going to the area that is dangerous. It's only similar, but you will understand that you need to apply something similar to the design of your product. In the presentation, you have several ideas about the elements in your product. For example, in PCBs, try to use more than 2 layers if possible. I know that for very low cost products, this is not possible, but if you can do this, going to 4 layers is a very big advantage. Partition at the PCB level too, not only at the product level. Ground planes, critical. Be careful in filters with parasitics, and where and how you do the layout of the filter. How is the optimum number of cables in a product? 0. Don't use cables. This is a joke. Sorry, but the real answer is use as less number of cables as possible, and these cables must be very short. They are the main problems typically in the frequency range from 30 megahertz to 400 megahertz. And of course, don't forget shielding. In shielding, except for high frequencies, for low frequency magnetic field, the problems came basically not with the material you are using, steel, aluminum, blah, blah, blah. The problems came from the slots and apertures and how you are going in and out of the mechanical design with your cables. There is a lot of books, there is a lot of courses about this. Suggestion number 6, be careful about low-cost equivalents, especially with components. Low-cost capacitors, low-cost inductors, okay? Yes, you are solving a problem with a sample received by from Würth Electronics. Now you try to find the equivalent that is low-cost in the market. Be careful about this equivalence. Many times they are not equivalent. The only equivalence is that they have the same inductive value. But for EMI, the resonant frequency, the saturation, the nonlinear effects, blah, 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 in many of these components are very important. You can see in the picture the difference between the real charger from for the iPhone, for example, and a very cheap alternative or equivalent. No, in red color you see how are the emissions, and in blue color you can see the emissions of the official or from the original design. No, there is a lot of difference between them. In the red color, we are creating a strong energy in the power supply network of your homes, and obviously for the same size in the case, there is a lot of thinking, there is a lot of design efforts to minimize the coupling and the emission of energy with this this AC/DC converter. Okay, don't forget safety. The bad device can go in fire very easily. Suggestion 7. If problems appear, remember our blocks. Culprit, victim, coupling mechanism. Okay, I'm going to finish in 2 minutes. Coupling, victim, and culprit, victim, and coupling mechanism. Where is the solution? The first solution you need to try is to kill the culprit. Try to find where the energy is created and try to kill this energy. For example, the energy can be created in a ringing, and using some specific ferrite bit, you can kill the ringing and the problem disappear. Not always. It's easy or possible. If the coupling mechanism is conducted, I mean, there is a metallic connection between the culprit and the victim, typically wires, the solution usually is to put a filter. If you put a filter in the middle, remember, filters work by reflection and by absorption. By reflection is when you are using inductors and capacitors. By absorption is when you are using resistors and ferrites. So remember, when using inductors and capacitors, the noise, the EMI, don't disappear. The EMI is reflected. In a very similar way, if the coupling mechanism is non-conductive, the solution can be sealed. So you need to put a metal seal in the middle, and part of the energy will be reflected, and part of the energy will be absorbed, exactly like with filters. There is a good analogy between filters and seals. Let's see the suggestion number 7. Think like a doctor. It's very important if you have problems. The most important part of the work of any doctor is the step number 3, the diagnosis. If you know what is the problem, many times you or any of your colleagues will find a solution. If you have a solution for your problem, the difficult part is not to find the solution, is to find a solution that can go to production. This is not easy many times. And my suggestion is at the end, explain how you have solved the problem to the people you are working with, because people want to learn, and this knowledge is very important that is not missed. Okay, so what is very important for the most important part of this process? The diagnosis. Diagnosis is the most important part. So what is very important for this part is the previous steps, is to understand what you are pursuing. Sometimes this is not clear, and to ask questions. It's important the doctor asking questions to know about the symptoms and to be able to make the decision of where is the problem. This is the diagnosis. Suggestion number 8, learn. And there is different possibilities to learn. You can read from books. For example, you can see here the book from Henry Ott, the best book for EMC, probably in general. Second, you can attend courses, online or presential. And finally, you can go to exhibits or conferences. This is the next conference we have in the IEEE related with EMI and EMC. Next year, this is 21. Oh, sorry. This is a mistake. I will solve this problem and I will change. This is the logo of the symposium for 2021. The 2022 is yet published. And in 2021, it was mixed with EMC Europe. We have 2 important conferences. The IEEE International Symposium on EMC and Signal and Power Integrity is usually in the USA. EMC Europe is in some of the cities of Europe. And this year was online virtual conference, and both conferences were mixed. A lot of papers, courses, seminars, exhibit from companies, a very good place to learn. And finally, put an expert of EMC in your life. It's very important in your design team to have some people, not perhaps very big expert, but people that is familiar with the EMI and EMC topics to be able to control how the progress is going. And if not, you can go for an external support. In the USA specifically, it's very common to have access to consultants. I have a lot of friends there, Ken Wyatt, Patrick Andre, Jerry Meyerhoff, Andy Eddy in Canada. We have Lee Hill. There is Keith Armstrong in the UK. There is a lot of people that is very good in helping. So don't forget to go to them. And thank you. That's all. So it's 55, so 5 minutes more than expected, sorry, but I will be happy to answer any question.
Thank you, Arturo. Amazing presentation. Thank you very much.
Thank you.
So, like always, we are fortunate to have you here with us. And going to the step 2 that you mentioned about question and asking things. Now let's go with the Q&A round, okay? So we have the first question is about the method you use to visualize the signal on the board. I think this is about the slide where you presented the board with the cell phone and the different EMC fields.
Yeah. Let me see this one. Let me see if I can find a slide that can show you the idea. This is the slide, I suppose. Yes, this one, okay?
Yeah.
This is a scanner where you have more than 1,000 small near-field probes, and there is the possibility to identify where you have the stronger activity of your product. So let me see if I can open here. I will try to find a picture. A moment, please. This one. Troubleshooting is very fast. Don't worry. With this kind of scanners, you are able to find where is the origin of the energy. This is one example. You have several of these scanners in the market. This is the slide I have, no? So the idea is you put the device under test on top, and there is the possibility to scan or to find where the problem is coming from. So, for example, you can be failing radiated emissions with this cable, okay? But you are interested in finding that the problem is coming from this area where you have a DC-DC converter and is coupling the energy to the cable, and then the cable is radiating this energy. So this is something like a version of the typical near-field probe that you can use for looking with your spectrum analyzer and a specific area that is aggressive. Let me remove this slide. So the advantage is that instead of moving the probe around the circuit, at the same time you look at the screen of the spectrum analyzer, here you have a picture that in colors give you feedback where you have the red area. The red area is the hot area, and then you can change things, no? Capacitors, firmware, inductors, or things like that to see the difference. More questions?
Thank you, Arturo. So the next question would be, what do you mean by reflection by LC filters?
By reflection means that when you are filtering, the idea is that if two systems are coupled, that means that if one of the systems is modeled in this way, and the other system is modeled like this way, one is the culprit and the other is the victim. If we have a good coupling between them, is because the impedance is in the order of one impedance is similar to the other impedance. So, for example, high impedance sources are very dangerous for high impedance victims. A high impedance system, for example, is a pin of an integrated circuit that is in open collector, no? It's not connected to anything, so it's high impedance. This kind of victims are very sensitive to high impedance sources. High impedance sources are sources with strong electric fields and smaller magnetic fields. For example, DVDT signals. Every time your system is doing a DVDT, your FPGA is resetted because this pin is being coupled very effectively, no? So one solution is to reduce the impedance connecting this pin to ground, no? So if you try to solve the problem with a filter, the idea is you are going to put here some element that create a new impedance. This new impedance must be very different to the first impedance. So for example, with one capacitor, we try to put one impedance that is very small compared with the CL. So the energy of the noise is doing this. The energy that is coming from the culprit, arriving here, find a low impedance path and is returned to the source. So it's reflected. The energy is not dissipated. If you put a ferrite in series, the idea is that the noise is coming through the ferrite and the energy is dissipated in the resistive effect of the ferrite, and the noise disappear. This effect is very well known by radio frequency designers when they have one antenna and they put in the output of the final amplifier a low pass filter, something like this. So the idea is that they want to amplify this signal. The amplifier create harmonics, and what you want in the antenna is only the carrier with the harmonics reduced. So my question is, where this energy is going? The energy is being reflected to the transmitter, to the amplifier, and can create additional problems. So in this kind of applications, it's common to do something like this, is to put a high pass filter and a resistor. This is a resistor, typically 50 ohms. So this energy that is being reflected is going here through the high pass filter and is dissipated as like a heat. That is what I was trying to explain.
Thank you, Arturo.
Well,
so next question would be, how much dBs can we decrease the conducted emission result by changing our PCB to 4 layers?
Conducted emissions is not easy to predict because the coupling to the cable for conducted emissions has a lot of possibilities, no? But for example, in radiated emissions, I have experimented many times reduction of 30, 40 dBs, 30, 40 dBs. So in conducted emissions, you can think that we will be in the tens of dBs because usually the idea of going to 4 layers means to have a very good ground plane in the areas where you need the ground plane, and the system go quiet very, very in a very big quantity.
Mm-hmm. Thank you, Arturo. I have a related question to this one. So what is the advantage of using high number of layers in PCB when compared to low number of layers in terms of EMI and EMC?
Considering emissions, the idea is that with a additional number of layers, you have the opportunity to dedicate some of the layers to ground. If you dedicate some of the layers to ground, first, you will have a lower loop area for your signals. That means there is no radiation from the PCB. And additionally, you will have the possibility to create a real good ground plane. One of the problems with ground planes that are not very good is that between two different points in the ground plane, you have noise voltage. And this voltage excites the cables that are connected to the PCB. So visually, you can think that you have a very good ground system, but this ground system is not very good. Let me show you the idea with this plot. No? If I have this ground plane, and for example, I have here this hole, or this hole are because I have in the same layer, I have here traces, no? So in general, what you see here is the ground, but the ground is interrupted because of these small slots, no? Consider, for example, that I have here a component and I have here another component, no? So in the top layer, I have this trace connecting one with the other. The return path for these signals is taking this path here. This is the return path. Why? Because there is a not real good ground plane below the red trace. And where is the result of this? The result of this is between this point and this point, let's say A and V, you will see in your oscilloscope something like this. This noise can be very small, some millivolts. Is related with the current that is in blue color, okay? So the idea is that if in this system we have a cable that is connected to the ground plane, this cable, for example, to point B, this cable is being excited by this voltage, and then you will fail in radiated emissions. If you have more layers, you have more opportunity to have a very good ground plane in one of the layers, a very good ground plane that is a very easy path for the return path signal, and then the noise is reduced a lot, and then emissions disappear. If you go to one layer, to two layers, or worse, to one layer, this is impossible in many systems. It depends on the complexity of your design, obviously.
Thank you, Arturo. So I think we have also a related question to this one, and you almost explained it. So it is suggested to separate grounds, like having analog ground, a digital ground, and so on.
No, it's not. The answer for this question, like I was explaining, is it depends. It's very, very difficult to say something that is valid for any design. But if you say to me, give me a recommendation, is if you don't know what you are doing, don't separate grounds. It's very dangerous to separate grounds because you will be creating this kind of voltages between different points of your system. No, a typical drawing that this can be explained the idea is something like this. This is my ground plane, and I am creating a separated ground for the digital and for the analog parts. Okay, so I have here a component, I have here another component, and in the top layer, I have this trace. This is the worst situation when you are crossing the slot with this trace. No, so the idea is, let me think what happened if, let me remove this, if I have two components. Let me remove this element and remove this element. Let me consider that I have this digital component connected to this digital component. And then this is the trace of my clock. And this is the sensitive area with two elements with their signals. No, so the return path is where? The return path is here. For the digital part, the return path is exactly below the upper trace. Where is the return path for the low frequency analog signal? It's something like this. It's a wider area, but it's below the upper trace. So why I separate the grounds if there is no possibility to common mode noise? Common impedance problems, the slot in the ground plane, the separated grounds, is a solution when you want to avoid the common ground problem. That means currents from the digital part are corrupting the analog area. And look at this. If you are in a design where in the placement, partitioning of the system, someone put this here, there is a possibility to common impedance because they are one close to the other. But if you separate the areas that can be related in the problem, there is no possibility of this problem. So why to separate? If you separate and you have some specific signal that is going on top of the slot, you will see that the return path is taking this path, something like this. And then between A and B, you will have a voltage drop. The A and B are 2 points of your ground system. And here I have the ground wire of your power supply, for example. And here I have the ground wire of my audio system. And what are you created? You have just created a dipole. So the solution to avoid the problem with the dipole is to join A and B. And that means to connect the two systems one to the other. Obviously, if your product is very small in size, perhaps you need to separate analog and digital ground, but then you know what you are doing.
Thank you, Arturo. So I misread the question. So it wasn't about analog and digital. So it was about analog and power ground. So, but I don't know if you would like to add something else. Or if it's...
This is you need to know what kind of currents you have. So the most important thing to consider the idea is that low frequencies return. Let me see. No, it's difficult for me to look for this now. But the idea is that if you have let me consider, for example, this PCB and this component, and they are connected in the top trace. Okay. And then I have a ground plane in the lower part. This is the ground plane. Remember, if you have a high frequency signal, the return path is exactly below the upper trace. High frequency means more than, let's say, 10 kilohertz. But if you look at the current in the ground plane when your signal is low in frequency means less than 1 kilohertz, for example, then the currents are doing this. That means what? In high frequency, currents concentrate below the upper trace. In low frequencies, less than 1 kilohertz, currents spread through the full ground plane. This is the problem that can be the reason to separate grounds, because in low frequencies, spreading around the PCB can create common impedance problem with other circuits. So you are considering to separate the analog and the power electronic grounds. That is because you are worried about the low frequency value of currents, and then you need to separate the grounds. But remember, you need to think about that. If you are not sure what you are doing, the best thing is to have a full ground plane and to separate the two different sections.
Thank you, Arturo. So I think I will read one last question during the live training, and then the rest of the question will be answered via email.
Of course.
Because we have a lot of them, so it's okay. So the question is about ventilation slots, if there is some recommendation on shape and size.
Well, this is a very broad topic, very fast. Always you have a frequency, a problem with some frequency. This is the frequency, so automatically you need to think about size. What is size in a signal is the wavelength. How much is the size? How big is a signal of a frequency f0? The wavelength in meters is equal to 300 over the frequency in megahertz. That means, for example, if your problem is at 300 megahertz, that means your size is around 1 meter. 300 over 300. So when we have problems in EMI, immunity, emissions, internal EMI, blah, 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 we have problems with the size of our system is in the order of the size of your signals. Solution: make systems, size of your systems must be small compared with lambda. So for example, if you are worried about the slot you are creating in your shielding between the cover and the enclosure and the body of the enclosure, and you have here this screw and this screw, you have two contacts, and this is the length. And your question, for example, is how many connections points I need in this position? The idea is that the maximum distance between the two connections, the maximum distance for this slot must be very small compared with lambda. If we have a lambda of 1 meter, lambda over 20 is a good number. Lambda over 100. It depends on how big you want the attenuation. Lambda over 20 for this example is around 5 centimeters. And it's for commercial application, this is a typical good value. Remember that in some applications, you need to go to lambda over 100. But if the size of this slot is 20 centimeters, 50 centimeters, something like that, it will be comparable to the lambda, and your signal will be able to be radiated. This is the general idea to think about this.
Perfect, Arturo. So thank you very much.
Okay.
Amazing presentation. A lot of thank you here in the question also. So thanks a lot. And yeah, so thank also to all the participants. Stay tuned. We are also doing further seminars. So I hope to see you all around. Thank you very much, and enjoy the rest of the day.
Thank you, Würth Electronics, for this invitation. Bye-bye.
Bye-bye.
Bye.